In this video, we're going to continue our examination of whether the bank is paying females and male employees different wages. But we're going to use more of the variables. Instead of, like in question 2, we estimated salary in a regression on the female variable, where female was 1 if female, 0 if otherwise. Here, we're going to include additional variables. And the variables we want to use are included in the regression table here. We want to have some college, BSBA, some grad school, grad degree, female, years 1, which is the years at the present bank. And then we're going to have 2 additional variables we're going to create. Okay, so what I'm going to do is I'm going to copy the variables one by one from sheet 1 into sheet 3. So the first variable I want is salary. I'm going to see if I can do it this way. Salary, some college, copy, and then right click, paste special values. There we go. So I got salary is the thing I want to predict. Some college is the first variable I want. Then I want BSBA. So I'm going to hotkey it here. Control-C, Command-C if you're using a Mac. Right click, paste special. The next one is some grad school. Some grad school. And then grad degree. Female. Years 1. And now I got to make 2 variables. The first variable I'm going to make is female times years 1. This is called an interaction term. Okay, so I want to multiply female, and that X means times years 1. So in H2, I'm going to type equal, then I'm going to get female, and I'm going to multiply with the asterisk by years 1. Okay. I'm going to auto fit these. Oh, let me get this first. Then the next variable I'm going to create is females times some graduate school. Your version of this might be different. Your version of the problem might be different. Okay, so you got to keep that in mind. You might have a different variable. We all have different problems, right? Now I'm going to click this box here between the A and the column headers and the row headers. So I'm going to click that box. And I'm going to come over here halfway between A and B, and I'm going to double click to auto fit. So this variable, I want to multiply female, the female value times asterisk, some graduate school. I'm going to multiply those together. And your column I will be different than mine, so make sure you keep that in mind. Okay, and then that creates the 2 new variables I need. Again, these are called interaction variables, and we'll discuss them more later. When we, so maybe we could do that now. Okay, so what this is, if the person is female, this is the number of hours or years a female worked at the bank. This person is male. The male worked 3 years at the bank. This female worked 14 years at the bank. This female worked 12 years at the bank. This female worked 8 years at the bank. This is a male, right? And then over here, if it's 1, if there's a 1 here, there's a 1 here. And what this says is this particular individual was a female and had some graduate school, right? This person had some graduate school and is female, right? And there's not very many ones in this column, is there? Right? There's not very many ones in this column. And these again are called interaction variables. And y'all probably have different versions than I do. I think everybody has this one, but everybody will have different versions of this. There's why I'm doing that, is I want everybody to have separate results, right? Unique results. And it'll result in different estimates, right? Okay, now we just got to run the regression. So I'm going to highlight the thing that we want to predict, salary. I'm going to highlight the thing that we want to predict, purple. And then I'm going to highlight the stuff that we're going to include in the regression, the X variables. We have multiple X's. I'm going to highlight that in yellow. Okay, so this is the thing we're predicting, and these are the things we're going to use to predict that, right? And obviously, we already know that female matters, right? We did that in question 2. So now it's just a matter of doing the regression, and it's the same procedure that we used in question 2. I'm going to click on Data tab, click on Data Analysis, and I'm going to find regression. I'm going to click OK. The input Y range are the salaries. So the way you can do this, you can click on cell A1. Then if you have a Mac, you hold down the Command Shift button. If you have a PC, you hold down the Shift Control button. You hold them down and then just hit the down arrow on the keyboard. And you can highlight all of them. So you should end up with A1 and A209 in the Y input range. For the X range, what you're going to do, you're going to click on cell B1, click it. Then you're going to hold down the Control Shift button if you have a PC, Command Shift if you have a Mac. Hold down those 2 buttons at the same time. Continue to hold them down. Hit the down arrow once, hit the right arrow once, and then you highlight all the X variables and their labels, right? So here you should have A1 to A209, and here you should have B1 to I209. And because row 1 are labels, we want to check mark labels. And then I want to keep the output in this sheet, in sheet 3. So I'm going to come up here to the top. We're going to put the output. We'll put it in K1. So we got K1 here. We got A1 to A209 there. We got B1 to I209 here. I got labels check marked, and then we can hit OK. And the results, I'm going to maximize this so I can format the results. Here are the results. I'm going to hold down my control button. I'm going to click outside here. I'm going to hold down the control button. I'm going to highlight everything that has a decimal place in the output table. I don't like scientific notation. Notice I left number of observations alone, the degrees of freedom column alone, right? I want to only set the decimal places on the numbers that have decimal places, right? And then I want to add 3 decimal places. Okay. Now I'm going to auto fit the table output. I'm highlighting K through P. Halfway between K and L, I'm going to double click on the line that separates K and L to auto fit. Okay. Now I can, yeah, that looks good. Okay. And then I'm going to come over here. I'm going to get rid of the confidence intervals, prediction and confidence intervals. So I'm going to highlight these cells out here. I'm going to grab the bottom right-hand corner, holding down the left mouse button as I do. To wipe out the confidence and prediction intervals. Okay. Now that's my regression output, right? This should be a review from Math 330. and business quantitative methods. If not, then it's a good time to learn it, right? Okay, my R square is just this value. I'm going to hit enter to see if I did it right. Okay, if I got that one right, then the chances are the rest of them are good, right? My adjusted R square is smaller. When you do multiple regression, you interpret the adjusted R square, not the R square. And then my F statistic is over here. It's in the ANOVA table. This is the test statistic we use to determine if the model overall is significant. And remember, a model is, that's weird. A model is significant if the p-value is tiny, right, for an F statistic. Then I got to insert my coefficients, the intercept of my model, and its p-value. My hotkey game is off. What I'll do is I'll just get my coefficients first. If you organize the columns like I did when I copied the data in individually from different from sheet one, then it's easy to copy and paste. You can just go one for one from Excel into my open math. It looks like some college is statistically insignificant. It looks like having a bachelor's degree is statistically significant. Some college appears to be insignificant, or some grad school seems to be insignificant. Grad degree, though, is significant. So if you graduate from grad school, it looks like you're going to see a bump up in pay. Female is significant. Years at the bank is significant. And so is females. The interaction of females in years at the bank is significant. But the interaction of female in some grad school is not. And that probably has something to do with the fact that some graduate school was, some graduate school is probably, I mean, you could say it's significant at the 15% level, but not the 10% level. All right, so there's my results. Let's double check to make sure we got it right. We'll hit submit. Hey, we got everything correct. Now we want to interpret the adjusted R square. So you go up and get the adjusted R square value. And the adjusted R square value says what? You multiply by 100, right? The adjusted R square says, or implies, 72.1% of the variation in salary can be explained by the model, that is linear in some college, right? BSBA, some graduate school, grad degree, female, years at the bank, and then the two intersection terms, right? So that's a pretty high percentage, right? Models aren't perfect. There are going to be some errors in the model, but this particular model explains 72.1% of the variation in salary, which is much better than the previous model, right? The previous version of this problem, we only had female, predicted, right? And we had a really small R square. My question got reset when I started recording the video. All right. The p-value of the f-test is really close to 0. So this is a long ways away from the hump of the F distribution. The hump of the F distribution is approximately around 1. And this is way out in the tail. So when this p-value is small, this F statistic is big. And what that implies is that collectively, these coefficients, all these coefficients here, collectively, their differences from 0 are highly significant, right? So we say the model's significant. The model's significant. If you had a p-value, if your p-value is bigger than 5% or 0.05, if your p-value is say 0.1, with your significance level being 0.05 or 5%, then you would say insignificant here. Okay. Now we're going to count the number of statistically significant predictors of annual salary. So I'm going to go through and count any of these p-values, not the intercept, that are less than 0.05. That's not less than 0.5. So I got 1, 2, 3, 4, and 5. I got 5 statistically significant predictors of annual salary. And I'll double check to see if I got it right. Cool, right? Some college does not predict salary, which kind of makes sense, right? Because, you know, a banker probably considers a person who graduated from high school and a person that finished 1 or 2 years of college to be kind of on the same level, right? Whereas a person that graduates from college, that's gonna raise your salary. People that graduated from college are gonna earn almost $3,600 more than people who did not graduate from college, right? Then some graduate school, that's not gonna affect salary. Grad degree, though, if you have a grad degree, you're gonna make, people with a graduate degree are gonna make $9,400 more than people who did not have a graduate degree, right? And then it looks like females are earning more. Wow, that's interesting. If you're female, you're going to earn $4,800 more than a male, which is weird, right? We didn't expect that. Each year you're at the bank, your salary goes up by $1,400. And then this one is significant too, right? So what's going on here is you got to subtract these two. So an additional year at this bank means you're making each additional year, you're losing $400 for each additional year, right? So that's how you interpret this female interaction. And I think we're going to do it more carefully down below. In question 2, females in the simple regression made less than males. I think it was about 9,000 less than males. But in this model, when we account for things like education, years of service, we're concluding that females at this bank actually make more than males, which is really interesting. And this is real bank information, I think from the 1980s. Okay, so having a bachelor's degree increases a bank employee's salary by what? Having a bachelor's degree. We're going around to 2 decimal places. Having a bachelor's degree increases bank salaries, employee salaries by that amount, right? Almost $3,600. Taking some graduate school courses increases a bank's employee salary by what? $0, because this predictor is, we concluded that it's statistically insignificant. That's why we put 0 here. Even though this coefficient is 5,800, roughly, it's statistically insignificant, so we put 0 down here, okay? Having a graduate degree increases bank employee salaries by $9,425.98 per year. The female coefficient implies that the average salary of female bank employees is more than males by that amount, almost $5,000. Each additional year of experience at the bank increased the average salary of males by, oh yeah, here we go. This is what I was talking about earlier. It increases male salaries by that amount, but increases it only by the difference in the sum of these two. So let's go over here. Sorry, I made a mistake on that. It's the sum of the two. So when I add these two together, I get the annual increase that females get relative to males. Now, the reason why that might be, you might find in this data that maybe females that are hired have higher levels of education than males. Maybe males start at the bank when they got out of high school, and maybe some of the females start at the bank after they graduated from college. And so maybe what's going on here is females on average start at the bank at a higher salary rate. So additional years at the bank, they're not going to get quite, males are being caught up, probably. I'm not sure. You'd have to survey the employees and really get into the data why there's a difference here, right? It's more than just looking at the data. You'd probably have to talk to people who do the hiring and promoting to figure out why this is. But it looks like each additional year, holding all the other factors constant, male salaries go up by much more than female salaries. It might be a performance bonus reason. It could be the way males in the 1980s and females in the 1980s negotiated salary increases from year to year. It could be due to discrimination, but I'm not sure about that because in our multiple regression, females are making more money than their male counterparts. There's probably 2 sets of females at this bank. There's probably females that work as tellers in the 1980s at these banks with probably a high school diploma. and some college maybe. And there's another group of females at this bank who probably have like graduate degrees or college degrees, and they earn more than their female counterparts who just got out of high school. And when you average them together and compare that to male salaries, you end up seeing that females are actually on average get paid more than males. The percent decrease from R square to adjusted R square, let's look at that. We're going from R square to adjusted R square. So we're going to calculate a percent change here. And the percent change is what is it minus what it was divided by what it was. And when you go from R square to adjusted R square, right? So we're going from R square to adjusted R square. Adjusted R square is what it is. R square is what it was. See that? And we hit enter. So the R square dropped by just a tiny bit. When you go from R square to adjusted R square, if you add a bunch of predictors to a model, you can artificially inflate the R square. So what adjusted R square is, it accounts for adding variables that may or may not matter. If this percentage difference is big, it's suggesting that you added a bunch of garbage variables to a regression to inflate the R square. But if this percentage difference is tiny like it is here, then the variables you added are, I guess you could say, valid in a way. They're meaningful. They're not ridiculous. Like, for example, if I added polar temperatures if I added temperature readings in Antarctica and the Arctic Circle to this regression, I could boost my R square, but my adjusted R square would be a lot lower than it. So if you just add a bunch of variables to a regression that may or may not be valid predictors of what you're trying to predict, in this case, salary, you can inflate the R square. But it shows up in the adjusted R square. If the things that you added don't explain salary, the adjusted R square will be a lot lower than the R square. So here, the difference between the two is 1.5%, a tiny amount. Now, because this says percent decrease, I don't put the negative sign in front of the 1.5. I just enter as 1.5. Yeah, so I had to fix the algorithm. The correct answer previously included the negative sign. And so I went through and I made the answer in absolute value. You don't need the minus sign because that says minus, right? Degrees. So this says minus 1.5. Now it works. Okay, so for practitioners, sorry, I'm getting, I talk too fast sometimes. For practitioners of multiple regression, a large R square and a large F statistic, a large adjusted R square and a large F statistic, and small differences in R square and adjusted R square are desired for regression properties. So if you're doing this, at a job, you want what you're looking for. If you're selling product for Amazon, for example, and you have regression models behind the data that you're collecting on consumers, what you're looking for is this to be high and this to be high, and then this difference to be kind of small. That's what you're kind of looking for. Okay. So that's what practitioners are looking for. These two, the difference needs to be small, this to be big, and that to be big. And that's exactly what we have here, right? Okay, so for the discussion question, you want to write a concise memo to management that describes your findings. In it, compare the results from the previous problem to the above problem. Explain why there is a difference and identify the more reliable results. Okay, so what I did is when I fixed the algorithm for this answer, I went back and filled in the answers for question 2. And in question 2, if you remember, I thought I filled them in. Let me reload this. Yeah, there you go. All right. So if you remember, the R square of the simple regression with only female in the salary equation, this value here implied that only 12% of the variation in salary can be explained by this particular model. So in this particular model, we found a difference in the male average and the female average. And that difference was a negative $8,000. Huge. But is that the only thing that matters when you're hiring employees, male or female, and then you're trying to retain? You're trying to retain those employees through time. Is that the only thing that matters? No, other things matter, like education, years of service, etc., right? The null hypothesis, in the null hypothesis, we're testing whether this was different from 0. And because the p-value was really, really tiny, and the test statistic was really massive in terms of absolute value, we concluded that this was statistically significant. The difference between this and 0 was highly significant. So we rejected this hypothesis. But again, only 12% of the variation of salary can be explained by this particular model, right? Because we're leaving out important information. If we go to the model with more information, we had the opposite results. The adjusted R-square says that 72.1% of the variation of salary is explained by this model here, right? We have more information that matters. Some college, it doesn't matter in this case. College degree matters. Some grad school, it's kind of marginal, but at 5%, we would say this is insignificant. Grad degree matters. Being a female matters. Years of service at this bank matters. Female interaction with years of service statistically matters, right? So I would argue that the more valid statistical results happen to be this one because more invaluable information is included, valid information is included in the regression model, right? The discrepancy we did see is that males were getting an additional $1,400 per year, whereas females were only getting $400 for each additional year of service. Again, that might have something to do with the fact that back in the 1980s, maybe most of the female employees started and stayed at the tellers, right? They remained tellers throughout their tenure at this particular bank. While at the same time, there is perhaps a bunch of female employees at this bank with graduate degrees and college degrees, but they're a smaller proportion of female employees at this bank. So we're averaging the annual pay raises of highly educated female bank workers with female workers who perhaps have been at the bank for a long period of time, who are tellers and perhaps are okay with that, right? So we probably have to dive into the data more deeply or ask very detailed questions to the bank manager, right? All right, well, that concludes interactive individualized lecture 6.